Good morning, everybody. Um, Welcome to this session about performance. Um, Here we are going to see some performance optimization schemes. We are first going to see a translation um, of Dask stencils into CUDA code, um, and we are going to see some, let's say, good practices to optimize this code um, on the CUDA source code, and we will mention then at the end which of these optimization schemes are actually implemented in Dawn, which we still want to implement. Um, and yes, this is to give you an idea of what the compiler can do other than just translating a high-level language into low-level code. So this is to really give you a full picture. And we are also comparing the performances that we obtained. We tried um, with some code taken from Icon, and we took some timings compared to the OpenACC accelerated version, um, and got some interesting results there, and we will see that in the last part. So the overview for today. So this is going to be this is going to be this morning. Then there will be a demonstration. I'm going to show you some the same optimization done live coding, and we will run our experiments on a node of a supercomputer. So this is I think will be hopefully interesting for you. Um, so we first go, first mention why GPUs, and we will give let's say a refresher about GPU architectures for those of you that already know about how these architectures work. For those who don't, this will cover the let's say strictly necessary aspects, topics that are needed to understand the rest of the presentation. So this is going to be quick, but keep in mind that this is much simplified with respect to the complexity of all the topics that are related to GPU architectures, um, and therefore it is not a comprehensive tutorial on how to write performant code on GPUs. Then we are going to define a baseline. That will be our reference when we do optimizations. Then we are going to present the optimizations that we studied, that we analyzed over time. And then we are going to see some numbers. As I mentioned, this code that we extracted from Icon. We will compare the baseline with all the optimization applied and so on, and against OpenACC. And then one slide about what is the current status of Dawn with respect to all the patterns that we will have seen. So a few words about GPUs. Well, this is clearly a good choice where we think, because in numerical weather prediction, you usually work with codes or problems that are inherently parallel. And well, GPUs, maybe they're not the only player in this, let's say, vector processing way of computing. But they are surely one of the big ones, and they provide very high throughputs, which is let's say the best way here to obtain performance. And yeah, maybe we can mention that at Matthew Swiss we spent a lot of efforts on GPUs. We currently run our operational model on GPU. So this is really important that also our DSL efforts go towards this direction. But this doesn't mean that Dawn or DSL should be should support only GPUs, of course, because you really provide an abstraction. But then what you do on the last level, on the last, let's say, on the code generation, this is up to you. This is just a component of your compiler that is flexible. You can add backends, and so you can support new architectures. But of course, we still want to be optimal on GPUs, and therefore, for example, Dawn IIR as a structure that reflects um, some specific needs of, let's say, vector processing in general. Um, and now I'm going to give you a quick refresher of GPU architectures. I will use NVIDIA terminology for simplicity, which is let's say the most common used terminology when talking about GPUs. Um, and we are going to see some, let's say, best practices when coding for GPUs, at least some of them, because of course this is an extremely simplified refresher. So let's start from basically saying how GPUs work on a very high level. Well, you both employ SIMD and SIMD paradigms. So single instruction, multiple threads means, well, in a, let's say, and this is not a formal definition, of course, but you spawn a lot of threads because you want to execute concurrently a block of code, which in the NVIDIA terminology is a kernel. And well, this is where the paradigm comes from: single instruction, multiple threads. And then in GPUs, there's also support for single instruction, multiple data, meaning that the same instruction is executed at once on several data. And we will see how. This is because well, you group your threads into vectors of 32. At least the architecture does that. So you take these 32 threads. These constitute a vector called warp, and this will be the granularity of SIMD. So all the threads in this warp will execute the same instruction in lockstep, so they will go through the same instruction. And well, of course, between warps, so between different vectors, there's not this guarantee. They might execute and will probably execute different instructions, but at least you have this vector, so this vectorization possibility native in the architecture. And at the very end of the block of code that you want to execute, so of the kernel, well, you are required to, at least the architecture is required to synchronize all the threads. So at the end, all the threads executing that block of code need to reach the end before you can call the kernel as executed as ended. So let's see a simple example of parallelizing a loop. So this is a very simple loop going from 0 to max -1, copying from array B to array A. If you would write this in with CUDA, for example, you would write something like this, where you have a CPU code and GPU code. This will be your kernel. So the NVIDIA compiler, for example, will compile each kernel that you define as a function. So they are the, let's say, atomic compilation. They are atomic compilation units. So they, let's say, the compiler wants look what you do with these kernels. They will be considered as, let's say, programs that you run on the GPU. And from the CPU code, you have this possibility to call them as functions, but of course they are not like any other function. And you need to specify somehow how many threads you want to spawn to execute this kernel. We won't go into detail about what is a block of threads. This is because, of course, we are covering just the necessary topic for the rest, so we don't need to know about blocks. Let's just think that this instruction here will spawn enough threads to basically solve this problem, to parallelize this loop. So we will have at least a number of thread which is max in this case. So if you look at then the code of the kernel, what you can do is you can retrieve the index of the current thread, and use this index to say, okay, is this index less than max? Then I can execute this instruction. So here is to not go out of bounds when copying. And you also use this thread to access memory. This is basically how to distinguish the computation. If you didn't have this number here, all the threads would execute exactly the same code with exactly the same data. So that wouldn't be useful. But here you can actually use the unique index of threads to actually map memory and do meaningful computation. So maybe the fact that I said before that well, some threads execute always the same instruction um, might not be that true, because as you can see, you can have conditional, so you can have um, execution with branches, so your code can follow different paths. So this is, let's say, divergence. We will not consider that in our analysis. You can just think of, you can just ignore when you see an if, because you can assume that most of the time this will be true. In just few particular cases, when you launch too many threads, you don't need to compute in that case. And since they are a very few example of that, it won't matter for performance. So we can just disregard the cases in which you don't follow, let's say, the main path of the code. So let's talk about warps and how they are executed. So let's say that you spawned 128 threads from 0 to 127. They will be grouped in vectors of 32. So you will end up with 4 warps, as you can see. And let's see a bit how the architecture will handle the execution of the warp execution. So let's look at this piece, a very simple piece of code. Assume that this is assembly code. We have 2 instructions, one writing into A and the other reading from A. Of course, you have a data dependency because the second instruction needs to wait for the operand A to be ready before start executing. So as we said before, threads within each warp will execute the same instruction at once simultaneously, while threads from different warp can execute different instruction. So in the architecture, you will have a warp scheduler, not one, of course. There will be many, but let's assume that again, this is a simplified explanation. Let's assume that you have just one. The scheduler will select which warp goes into execution at each, let's say, warp cycle, at each cycle. So at each, let's call it time step of time. And well, it will choose which warp goes into execution with which instruction, of course. And this warp comes from a pool of ready to go warps, meaning that the next instruction to be executed for that warp needs to have the operands ready. So a very simple example here, if you want, say, warp 0 to execute the second instruction, you must make sure that it has already executed the first one because of this data dependency. So in order for warp 0 with instruction 2 to be in the pool, instruction 1 for warp 0 must have executed already. So the data dependency should have been resolved. So this is the example. This is a possible warp execution. Here you have time, you have your cycles. At each cycle, the warp scheduler will issue the execution for one warp and one instruction, of course. So of course you will start from the first one. And for example, you could the warp scheduler could execute in this way, going from warp 0 to warp 3. And after 4 cycle, you have issued the same instruction for all the threads. But then you need to wait. You need to wait because you need to wait that's the for example, the first warp that for which you issued the first instruction finishes, because, well, you are out of warps, let's say. Here you issued the first instruction for all the warps, and you cannot execute this instruction because you need to wait for the first to be completed. And this is a stall that is due to the latency of the instruction. Let's see, and this is important because, as we said, GPUs are throughput oriented, and this kind of stalls will limit the throughput and thus the performance. And if you can do something about this, this is very good, because the more you reduce the stalls due to latency, the more you can increase the throughput. So for example, what you can do is increase the number of threads. Of course, you need to think about the problem that you want to solve, and probably rethink your algorithm in a way that it separates the problem in, let's say, multiple, the problem in such a way that it can be solved with more threads, so it can be parallelized more. Let's say that you double the number of threads and thus the number of warps, but you keep, let's just keep looking at this piece of code for simplicity. What will happen is you will reduce the stall due to latency just because you have more warps, as you can see. Another way to basically achieve the same result, which is reducing stall due to latency, and this is called latency hiding, is let's imagine you have, in this case, just the 4 warps that you had before. Imagine that you had an instruction in here that is completely independent from the other 2, but let's say that you needed to execute this instruction anyways. This is the assumption that maybe this was another computation that you needed to do afterwards, and then you place it here. This has no data dependencies with the others. And what you can do is, after you issue the first instruction for all the warps, you can issue the second instruction, and it will execute in parallel with the first. And this is called instruction level parallelism. And you can do that, for example, with pipelining. So the architecture has this pipelining that is basically a technique to make more independent instruction execute concurrently, but we will not go into detail into that. It will take a lot of time to explain, but so just trust me that you can do that on GPUs. And you basically achieve the same result. So you can reduce your stalls that are due to latency and increase the throughput. So let's talk about memory on GPUs. You have different kinds of memory. Of course, you have registers. You have a pool of registers in your architecture that is then divided by the number of threads that you spawn. And each thread will have a set of registers that are dedicated to the thread. Of course, they are fast, but they are limited. There are not many threads. You have main memory. and caches, which we can simply consider as much slower than than registers, and other types of memory which we will not talk about. So as I mentioned, access in main memory is slow. Of course, this is a simplification, but maybe you can do something to optimize your let's say your accesses to memory. And this you can do by minimizing the number of memory transactions, which will increase the bandwidth that you use. So what the architecture will try to do is within each warp, so within the 32 threads that we mentioned, see how these threads access the memory each time some data from memory is needed. Let's say the architecture will collect the addresses of memory that are accessed, and will try to coalesce these accesses into as few as possible transactions. Of course, transactions will copy, let's say, will transfer from main memory consecutive blocks of memory, so with nearby locations. Here, this a simplified picture in which you have 4 memory locations which form a transaction. So in this case, this arrow will make the architecture transfer just two blocks, so 2 transactions. How can you achieve this? Is by, for example, a sequential access pattern. So sequential threads in a warp access sequential memory locations. An example is you have thread number 0 of the warp that accesses memory location 0, thread number 1, memory location 1, and so on. This is, let's say, the optimal way to access memory. So if you can, you should design your code to basically use this pattern. Of course, this is not always the case. In some case, you just cannot do that. And an example of non-optimal memory access pattern is that of a strided access pattern. Say you have a stride 2 in your pattern, so you skip one. In this case, to, let's say, access the same data that you need to transfer 4 blocks, so 4 transactions instead of 2. So you can imagine that here the transaction performance, the usage of bandwidth, let's say, is the usage of bandwidth is doubled. So the actual performance of your memory access is cut in half. Let's spend a few words about memory hierarchy. So as mentioned, you have registers, you have main memory, but you also have caches. So as we already said, registers have low latency and highest bandwidth. So this is what I said before. They are fast in this sense. They have low latency, the highest bandwidth, but they are limited, of course, while main memory is the exact opposite. They have the highest latency, the lowest bandwidth, but you usually don't have a problem in terms of capacity. Caches are middle ground, but they are closer to registers. So their working principle is to temporarily hold the data that comes from main memory, so that when you maybe access the same data again, you can already find it in the cache, and it will be much faster to access it there with respect to main memory. And this, let's say, the efficiency of caches, so how likely you're going to find what you are looking for already in the cache, with respect to, let's say, not finding in the cache, so having to retrieve the same from main memory. This depends on some, let's say, statistical assumption that you can make, and then of course this statistical assumption, uh, you should make them true by let's say let's say thinking about your code in a way that these become true, and we will see later on how to help in this matter. So these assumptions are locality. You have temporal locality, meaning that recently accessed memory locations are likely to be accessed again in the future. So if, for example, at time 0 you access this memory location, and this assumption is that basically it's in the near future, time 1, time 2, you will access the same. And if this is true, then well, the cache most likely will have already that data stored. Then you have spatial locality. So since since data is transferred from main memory to cache in consecutive blocks, so in contiguous blocks, and this will mean that if you transfer the block which contained this memory location, you already have in the cache available this and this, and if you happen to need those, you already have them in the cache. So this is another let's say nice feature of a code. If you can exploit the data locality, the spatial locality, you can basically increase the efficiency of usage of caches and thus increase the performance. Okay, so this concludes the a refresher about GPU architectures. I hope everything is clear. Otherwise, we can address some questions, of course, in the Q&A afterwards. Let's reiterate now a bit about the parallel model that I presented yesterday. But let's go very quick. So we already said that if you write a Dask stencil, there is, let's say, a simple way to execute it, which is, well, you iterate through the k levels going from bottom to top sequentially. Within each iteration, I'm looking just at this example, you copy field A over the whole horizontal domain into field B without assuming any order in the copies of the at each of the location. And then the same after you did that, the same from field B into field C. And again, I want to reiterate that you have API fields, which are part of the contract with the user. And you have temporary fields, which are like local variables. Here, the compiler has leeway, so you can maybe inline them, and we will see some cases afterwards. So let's define our baseline. This will be a way to translate a Dask stencil into CUDA code that is already valid, that you can compile with NVIDIA compiler and run. This will already give some nice performance because it's already parallelized sufficiently. But let's say this is a naive and simple translation, and you can start from this one and apply the optimization that we will show afterwards. So let's first make an assumption. There are no vertical data dependencies between statements. So let's simplify our problem. Like as you can see here, you don't access fields at k-1 or k+1 and so on. So you can basically switch the loops between the horizontal and the vertical. In this translation, which is very close to the parallel model, you are going to have to write one kernel for each statement. So you will have, for example, for the statement 1, field B equals field A, you are going to write this kernel, and for statement 2, field C equals field B, this one. And one CUDA thread, so one thread is going to perform the computation for a location of the horizontal domain. So in the case attend, it is going to compute the copy for one edge. Another thing to mention is that here the for loop over k is repeated inside each of the kernels. And this you can do because of the assumption of no vertical dependencies. Okay, let's talk a bit and this we refer to what already said before about memory organization, how you organize your fields in memory. So as we have seen, we have dense fields and sparse fields or sparse dimension, I think we also call them. If you store your fields as multidimensional arrays, linearly stored in row major order, already an optimization that you can do, and we already do this in the baseline because it wouldn't be, let's say, meaningful to not do it, is to put as last dimension the dense dimension, so cells or edges or vertices. And this is because we want to obtain coalesced accesses. So what I mentioned before, here you basically obtain a sequential access pattern. Thread 0 is going to access a field for say vertex 0, so thread 1 for vertex 1, and so on. So this will let's say minimize when you access a field at the center of your stencil. This is going to minimize the number of memory transactions. How to translate sparse iterations? Sparse iterations we don't parallelize. So we put a for loop inside the kernel that will go through the neighbors. And here I'm talking about, for example, reductions or sparse loops, the concept that you saw with which you can write into a sparse field. They are translated in the same way. You have this loop over your neighbors. So we are looking, for example, a cell edge iteration space. In this case, you have, of course, 3 neighbors. So this NBH iter is going to be 0, 1, or 2. So it's your neighbor number if you want. Then we have this neighbor table. This is going to give us the index of the current neighbor, starting from the neighbor number, so 0, 1, or 2, the index of the current cell in this example, but in general the index of the current dense iteration. And of course here you use the thread index because, as we said before, this represents our way to map data, and it corresponds one-to-one with, in this case, the cell index that we are processing. You use the neighbor number and the index of the current cell to access the cell to edge table in order to retrieve the index of the current edge neighbor. And then you use this index to do your computation, for example, to access a field on edges, or a sparse field, or so on and so on. Maybe I can mention that this neighbor table is stored in memory like this. First the dense dimension, then the neighbor dimension, but I will not go into detail why this is already optimal. So before we take some questions, I wanted to outline this tool, the Roofline model. It's a visual tool to basically evaluate, let's say, how well you're using your say the architecture, the memory resources, the compute resources, and it's a way to maybe predict how much an optimization can improve your performance. So let's briefly describe it. It's a visual tool, so you have a plane. On the x-axis, you have the operational intensity, so the number of floating point operations that you need to do, divided by the memory traffic, so how many bytes are exchanged between memory and your compute resources, so your um, arithmetic unit and so on. And on the y-axis, you have the performance that is measured in flops or gigaflops per unit of time. Of course, each architecture has a peak performance, and these will be, let's say, the theoretical limits. Let's say if you use at the maximum all the compute resources, you will be at the peak performance, and really you cannot go over that. This is the maximum bound that you can that you will hit. And if you are lucky or very clever, you can reach the compute bound. You can optimize so much your application that it reaches the compute bound, and this is the maximum that you can achieve with that specific architecture. Then, of course, there is the memory bound, and 99% of the time you are going to be below this line because, well, memory is usually the bottleneck. Bandwidth is the bottleneck. But you can still do things to optimize. There are, let's say, two orthogonal directions here in which you can optimize. One is increasing your operational intensity, and we will see how. It's usually done by reducing the overall memory traffic while computing the same amount of floating point operations, so that you go towards the right and you are less and less memory bound. Another very good way to gain performance is, as mentioned earlier, to hide latency. But in this case, you don't actually change the memory traffic, you don't spare memory transactions and so on, and so you don't change your operational intensity, you just go up. Okay, so this concludes the first part. Now we will take some questions.
Thank you, Giacomo. Maybe I can post the link to the questions document real quick. Let me see. And then we can give people some time to type up their questions. So I will post the link in the chat. Okay. Yeah. Yeah, so I think we can give people a little more time, but if there's no questions, then we can probably continue. So let's just wait 1 or 2 more minutes. Oh, now we have someone typing. Let's wait till they manage to type out the question, and then we can look into this. I will read the question real quick. So David is asking, in the parallel model, is there support for multi-GPU?
Okay, let's say that's what we presented is maybe a simplified version of the parallel model. And in that simplified version, I would say no, but since we still haven't, so in the parallel model that we have implemented in Dawn, there is the possibility to support multi-GPUs. But let's say we still haven't considered that for unstructured stencil. This is a next step. But was already considered for lat long grids, so structured stencil that don't support can still support. Um, and yeah, for unstructured, we are still not there. But we still have to keep in mind that this is the next step. So I hope
Maybe
that answers
I
the
can add
question.
a comment to that as well. So, I mean, with multi-GPU, you would probably need to do halo exchanges between the GPUs, right? And maybe if you do that right, then the parallel model should kind of naturally extend onto multi-GPUs, no?
Yes, I think that is true. Yeah, you can assume that when you have synchronization, this is across multiple GPUs. So um, still you can optimize it further by doing redundant computations. But okay, maybe in a simple model like the parallel model, uh, if you assume synchronization that you have these halo exchanges and so on, this already is covered by the parallel model actually.
Okay. I hope that clarifies that, David. And I see no more questions.
Okay, thank you. To start the timer. Okay. Yeah, 1 second. Okay. So let's start talking about the first optimization that you can do, starting from let's say our baseline translation. So we said before in the baseline, you translate each statement with one kernel. Um, so you can think of joining together two statements to be executed by the same kernel, but you can do that according to this optimization only when both statements are run on the same iteration space. So either edges or vertices or cells. In this case, that in this stencil that you can see here, we have two statements, both on edges. This you can derive from looking at the fields, how they are defined. So we can think of joining together the two kernels. So fusing dense loops. Loops is within quotes because, of course, they are not loops anymore. They are parallelized, so they became kernels. And in this case, this is very simple. You just put together the two instructions nest them within the for loop over the k, of course. And well, let's see why this is an optimization, why this helps in improving performance. Let's first make the assumption that there are no data dependencies between the statements. And of course, this means that as I told you before, you can use this if you have independent statements. You can put them together, let's say in the same translation unit, so they will end up being in the same assembly. And you can use that to employ instruction level parallelism to hide latency, which is one of the best practices for increasing performance on GPUs. You also gain from not having to do any kernel level synchronization, and this you can do because they are on the same iteration space and now on the same kernel. You share the K loop, maybe you also gain something from that. But let's say the major benefit is really hiding latency. In this case, you don't spare any, overall, you don't spare any memory access. So no, the traffic with memory is unchanged. So is the operational intensity. It's not, it doesn't change in this case. This is the exact same as same case as before, but the second statement is now a reduction, but it's a reduction on the iteration space edge vertex, which means that this statement must be executed over each edge, and then you loop through the vertices. But again, the iteration space, the dense iteration space, is edges. So you can join it together with this simpler statement here, as you can see in the fused kernel. And this is, of course, the translation of the sparse iteration. You're computing a sum. So you really store into this sum the, in this case, it's very simple, just field C accessed through this neighbor index. That we retrieve from the edge to vertex table. And then this sum goes at the end after the loop into field D, as you can see. And these together, these you can put together in the same kernel. And again, the benefit is hiding memory instruction latency and memory latencies, because some instructions are load instructions and they have a very long latency. So another case of fusing dense loops is when you have non-offset data dependencies, meaning that you read from a field, and in this case I want to remark that this is temporary. You read from it, let's say at the center of your computation. In this case, you don't even have a reduction. So you really are just copying it. And so if you have a non-offset data dependency between two statements that you can fuse because they are in the same iteration space, this optimization is even larger benefits, because in this case, and keep in mind that you can do it, you can do this because field B is a temporary. You can just remove the temporary, store the result of the computation of the temporary into a local variable, which is in the architecture is going to be a register, of course, except for particular cases. We will mention that later on. And you can use this local variable to do the next computation. Here we are looking at extremely simple codes, and this is for better visualization. But I ask you to imagine a more complex one, and but isolate, let's say, the property that we are describing, that we have the same iteration space and in this case a non-offset data dependency. In this case, we increase the operational intensity because before you had to write into temporary, so into allocated memory. So you had to go through memory, write, and then read in the next kernel, which meant a lot of um, transactions of memory transactions. In this case, you just remove that part, so writing into field B and reading from field B through memory. You just do that with registers. So you spare a lot of memory access in this way. Same case as before, but then this time I changed the first statement to be a reduction, just to show you that you can store the result of the reduction instead of into a field that is allocated in memory into a local variable that you can just use then for the next statement. Again, same case as before. Now the second assignment is a reduction instead. And what you do is the same. You store local field B into a local variable to do the computation, and then you use it within the reduction. So maybe keep in mind that this is access non-offset because this is a field, field B is on edges and not on cells. So you access it at the same edge in which you computed it in the current kernel. Okay, so what if instead you have field B that is on vertices, and it's a temporary. You do some computation that you store into field B. So for each vertex, you write something into field B. And then you need to use it from within a reduction from, say, edge to vertex. So, and now you access field B, but you access it offset, meaning not at the center of your computation, which would be an edge, but on a vertex neighbor of an edge. So there is an offset data dependency. And in this case, if you want to bring this together into the same kernel, we don't say this is fusing a dense loop because now the iteration space changes between these two statements. One is on vertices, one is on edges. What we call this is now stencil inlining. And since this temporary is only consumed once, it's only read once, it's one time, so a particular case, of course. We remove the pre-computation, we compute it from in the place where it's used, so that we don't need to go through memory, same as before. So similar benefits of fusing dense loops with non-offset data dependencies, but there is this major difference that is due to the different iteration space here. Of course, operational intensity increased because we have less memory traffic and so on. So maybe to give you an idea visually, you just nest the computation inside the loop. And here you just do your computation store into a local variable and then just use it. Okay, this would be the same case as before, just a bit more complex. And here we should probably mention that this optimization is not always an optimization in the sense that it could degrade the performance, and I will mention why. But let's first see what happens here. So let's imagine the case in which we have two reductions. In the first statement, you have this reduction which writes into a temporary. So in this case, it's a cell to vertex. So this statement is executed for each cell, and then you iterate through the vertex neighbors. And then this data is used from within a reduction edge cell. So this statement is executed for each edge, and you loop through the cell neighbors of the edge. And within each iteration of that loop, you would access field B from memory in a let's say in the naive translation of the baseline. What you could do is nest together this reduction, and we mentioned that yesterday that this is not currently supported in Dawn, but this is to give you an idea of how it would look like. And of course, the second statement is the outer reduction. Then inside you have the inner reduction nested within each iteration. Now you need to distinguish between the neighbor index of the outer, which is an index of a cell, neighbor of an edge. Then you will use this neighbor index to access the inner neighbor table from cell to vertex to retrieve the neighbor index of the nested reduction of the nested iteration, which is the index of a vertex. You will use this neighbor index to access a field, field A, which is, of course, on vertices. Then your optimization here would be to store the intermediate result, so the output of the inner reduction, into a local variable, which you then use to compute the outer reduction. Okay, maybe one remark here. Before we mentioned caches, locality, and so on. So why is this optimization not always good? This is because if you didn't have this inner reduction in here, well, the outer reduction would store the intermediate result. Sorry, would make use of caches for storing, let's say, neighbor indices or accessing field B. And if instead you nest these reductions, so this loop and a lot of accesses inside, you could basically flush the cache, because of course the cache is limited, and therefore make it not convenient to do this optimization. But maybe this is let's say an advanced consideration and needs some more complex modeling, so we will not go, of course, into detail into that, but just keep in mind that here you could improve, but you could also degrade your performance by doing this. Another type of optimization is fusing reductions. So let's now assume that you fused kernels together for these two statements. So they are on the same kernel. They happen to be two reductions on the same iteration space, vertex edge. And if you just did your optimization of fusing dense loops, you would end up with two for loops, one after the other. So you could think of bringing them together. So one for loop in which you do both computations. As you can see here, what you gain is from sharing the access to the neighbor table. You need to access it just once per iteration to do both computations. And if you are even luckier, you can share the accesses to input fields which are in common. In this case, both computations are reading from field A, and at each iteration of the for loop, right? So you can just think of storing into a local variable, so a register, and reusing it twice. Okay, so of course, this due to this sharing of accesses, you gain into reducing the number of transactions again, the traffic with memory, and therefore your operational intensity has increased in the Roofline model. You also have some infrastructure in common, like the for loop, and this also is you gain something also from that. Okay, it's not only about reductions, of course. There are also sparse loop, the with sparse statement that you have seen yesterday, in which you can use this concept to write into a sparse field if you want to compute into it. You can fuse that together with a reduction or with another sparse loop, because their implementation, the one of the reduction and of the sparse loop um, in the generated code looks very similar. You still have the same loop if they are, of course, on the same iteration space, the same access to the neighbor table, but then in one you write into your sparse field, while in the other you compute maybe a sum that you then write at the end into a dense field. So this optimization, of course, would be the same as before, just bringing them together within the same for loop. You gain more if while doing this fusing of sparse loops, this case happens. So let's imagine field sparse is a temporary. So again, you have a leeway what to do with it. You can inline it, and this will correspond to inlining, of course, doing this fusing. So instead of storing into field sparse, you just demote it to a local variable, and you just use it in the next step in which you are computing the reduction. So you don't go through memory, you spare a lot of memory accesses, and so on and so on. Okay, of course, the inlining that we shown so far are very simple and optimistic, because well, you write into your temporary and then you just use it once. This is I think most of the time not the case. So let's see a more realistic example in which you have a field B, for example, again a temporary, that you consume at least twice. So you have two reductions in this case on different iteration spaces. And keep in mind that this statement is on edges, this is on cells, so you cannot fuse them together. They must live on different kernels. And on both you consume field B. And in the baseline translation, of course, you have three kernels, one computing field B and the other two consuming field B. So here you can think about inlining, but this will mean computing the right-hand side of this multiple times, which means artificially increasing the number of overall floating point operation that you need to do. If you can imagine that this is this improved performance. But let's remark here that it can improve performance, but under some circumstances, it's not always the case. And here you really have to do an analysis. The compiler will need to decide whether to do this optimization on a case-to-case basis. Um, so here you can see how it would look like to inline field B. You again compute into a local variable, and you compute basically the same quantity on both cases. Okay, let's try to um, let's try to um, uh, do this kind of analysis that a compiler would need to do. But let's make some assumptions, some really heavy simplifications, approximations, let's say, um, to have just an idea of how it would work, like an heuristics that you could implement in a compiler. But of course, this is not going to be general. This is just a simplified example. Let's, for example, ignore that you have caches. So ignore the effects of caches. And what this means is that if I'm counting the memory accesses, um, I am weighting all memory accesses the same. So this means that I can count, okay, in this code there are 2 memory accesses per vertex. But of course, this will not be true if you add caches, because well, a memory access to something that is already in cache is much more cheaper than memory access to something that is not in cache, that you need to retrieve from main memory. So this model of counting accesses in this way only works if you can ignore the effect of cache. So this is the first simplification. The other simplification is that we are considering additional floating point operations that we artificially introduce as, let's say, extremely cheap again. So we don't consider them in the count of this cost function that we are basically computing. And this, of course, is a simplification, because clearly arithmetic operations have a latency. It's much less than a latency of a memory operation, but it still should count. So under these two simplifications, we are going to count the number of overall memory accesses needed on the left, so not doing the recurrent stencil inlining optimization, and on the right, if we do such optimization. So in this case that I shown you before, if you count, you get 2 memory accesses per vertex, 3 per edge, and 7 per cell. If you do the optimization, you strictly improve, because you have 0 memory accesses per vertex, and the same as the left case for the other location types. So the heuristics will tell you that it's better to do this optimization. In this other case, so this is a more complex one. Again, you have a temporary field that you use multiple times, but this time this computation is much more heavier, in the sense that it requires you to sum 3 fields. It's very artificial, of course, but you can imagine to have something that looks like this. So a much heavier computation, and then this field temp is used 3 times, is consumed 3 times. So what you will need to do on the right is, again, nest this computation each time, and that gets quite heavy. You need to recompute a lot. And if you count the overall memory accesses here, the left is strictly lower, and therefore the choice here will be not to do the optimization. So a last case, in this case, you have a temporary, which is a sparse field. So edge to vertex, for example. And now you have this computation into the sparse field with the sparse loop concept. So you compute it twice for each edge, because you have you store into this field twice for each edge because you have two vertex neighbor for each edge, and then you use this value two times. While if you did it, if you apply the optimization, again you inline this in the reductions. And in this case, if you go counting the memory accesses, they are all statements on edges, so you only have you count memory accesses per edge. You can see that on the right you have less, strictly less. So maybe for a sparse field, this is inlining multiple times a sparse field could be much convenient than inlining multiple times a dense field. But of course, this still need to go through this uh, analysis through an heuristics, which is again maybe simple, maybe too simple, but it's just to give you an idea of how you can um, how you can um, construct a decision process based on a cost function. Okay, so regarding the optimization that I presented so far, we saw that basically you could bring together computations in the same kernel, but this means in general that the number of necessary hardware registers to do these computations could increase as a natural consequence of keeping memory transactions to the minimum. So if you don't read and store to memory, you are reading and storing to registers. So in general, the consequence is that you need more and more registers. So maybe virtually you could increase the number of registers up to infinity, but then the hardware is going to have a limited number of registers. And this is another limitation that you can have. What happens if your virtual number of registers per thread exceeds the number of available registers per thread? So the data that would have been stored and read from these registers would be spilled into main memory, which is basically going backwards to unoptimizing, because it's the first thing that we wanted to avoid. We want to read the story into registers because they are much faster. While if you have to go back to main memory, you are not optimizing anymore. So there is a limit to how much you can fuse kernels together, you can fuse computations together. And at some point, you certainly need to stop because of this limit. But maybe to just give you an idea, empirically, we saw that we, in our experiments, we never reached this limit. But it's still, of course, important to keep an eye when you do optimization on the register pressure, on how much registers are you using. Are you at the limit, near the limit? Do you have to stop using kernels? And so, of course, this is also important to question. Another limit is data dependencies. Well, of course, you cannot fuse at your will just because statements are on the same, let's say, iteration space. So let's see an example. You have these two statements. They are both on cells, as you can see. So the two kernels that are on cells in the baseline translation. You could think, okay, I can fuse them together in the same kernel. But if you look, of course, at the code, you see that there are data dependencies. So between statement 1 and statement 2, there is a write after read data dependency. So this means that, well, you need to, since the second statement is writing into field C and the first statement is reading from field C, you need to wait before you can start executing statement 2. Otherwise, statement 1 will have a spurious read. And instead, between the second and the third, you have a classic read after write data dependency. So the what you have written into field C is read by the statement below. And due to these constraints, you cannot really fuse, otherwise you will end up in incorrect computations. Okay, let's see this other optimization that we mentioned a lot yesterday, parallelizing the K-loop. How does it look like in CUDA code? Well, of course, this corresponds to having more threads, so spawning more threads, because now you need not only to have one thread for each location, but you need to multiply that by the number of K levels that you are parallelizing over. So you can think about the indices that you have. So you might have this PIDX index that is, as before, the index of, say, an edge. In this case, you have this computation over edges. And then you have KIDX, which is the index of a K level that you can then use to access your field at that specific level. So what happens here is that one CUDA thread will perform the computation for one location, in this case an edge, and for one K level, while before it performed, so in the baseline authorization, it was performing the computation for one location and for multiple K levels, because inside you had the for loop. Now we removed that for loop and shifted the looping to the threads, so to the additional threads. So what is the major benefit? Well, of course, we increase the number of threads, and this hints that the major benefit is in hiding latency, as showed before at the beginning of the presentation. Then we will see later on if this actually happens. But of course, the memory traffic is unchanged. The overall memory traffic is unchanged. So is the operational intensity. We are not using less bandwidth. So one last optimization. Well, sometimes you just have vectors. We don't currently support in Dask, as we mentioned yesterday, but you can just write the components of a vector u and v, as you did in the exercise, I think. So what if you recognize that this is actually a vector? You could load it at once with the same load instruction into a data type that is provided by CUDA, which is, for example, 2 in this case. Well, of course, the amount of data transferred, the memory traffic is not changed. You are still transferring the same amount of memory as before, even if you, let's say, access it with the same instruction. The number of bytes transferred is exactly the same. What you gain here is you have one less load instruction that covers more, that covers, let's say, a larger segment of memory, and this can improve performance. Okay, let's jump to the questions.
Thanks a lot, Giacomo. So there was one question from Will. I will just read this out. Sorry for my confusion. You keep saying operations can be fused. By this, do you mean simply that the user puts the operations within the same with statement, and Dusk Dawn is responsible for automatically fusing the operations? but then you mentioned that some of the fusing is not yet supported within Dawn. So the question is, what sort of fusing is currently performed by Dawn? Are most of these optimizations foreseen for the future?
Okay, maybe this I will tell it on the last slide, but maybe I can just anticipate. The dense loop fusing is already done by Dawn. Sorry for the usage of words. But the user doesn't need to put the operation in the same with statement. This we assume that basically the user can express the algorithm as preferred, as in the most readable way possible. Then it's the total responsibility of Dusk and Dawn to take care of doing the best optimizations and maybe bring this to a canonical form and then optimize. And maybe to answer the last question, if these optimization are foreseen for the future, I would say a big yes, because we saw and we will show that nice results from applying this manually, and we want Dawn to support this, all of them. I hope that answered the question.
So there's another question being typed. We'll wait a bit to give Thomas some time to type it out. And it looks like Will is happy with this answer. So I think I'll start reading Thomas' question. I'm not sure if you're finished typing out the question, but there's already some part that I can maybe read out. So right now, these optimizations have to be done afterwards by hand directly on the CUDA code. That's the question by Thomas.
Okay, actually, no, we support some of them in Dawn, but since this was about presenting, let's say our study about those, yeah, well, since the other are not supported in the demo afterwards, we will show them by hand. But of course, the ultimate objective is to have Dawn support all of them. So as you will see in the demo, with Dawn, we get pretty close to the performance that we get by just doing them by hand, because let's say the most important ones are supported. Then the rest, it's just an implementation gap. Percentage improvement, I would say. Well, this of course depends on how you choose your baseline, your reference. If you go from the baseline we saw, it's can be also a big improvement. You can get to one third, for example, of the time. Could take one third of the time if you under let's say the correct circumstances, but clearly depends case to case. And of course, the choice of the baseline is arbitrary. One could choose as baseline an OpenACC version of the same code, and we will also see one example of that in the next part of the presentation after the break.
All right. We are a little slightly behind schedule, but I think that's kind of okay. I think we can wait like a little bit more time to see if there's any more questions. And then otherwise we will be probably heading into a break until 11 if I got the agenda right. But let's give it a little more time if someone wants to add a question. Yeah, so thanks a lot for the presentation so far, Giacomo. I think there don't seem to be any more questions. And then I think we will be heading into a break, and we will reconvene at 11. So back to you, Giacomo. Thank you.
Thank you again. Okay, well, let's resume from the break, and let's go into the next optimization. So maybe let's explain a bit the context here. This optimization is something that is outside of what the compiler can do. So this is not a concern of the compiler actually. And this is more a concern of the user, or rather the meshing library. But still, in our study, we wanted to really get the maximum performance out of stencils, the stencil that we tried, and we explored all possibilities. And we are still going to see why also the meshing library matters. And maybe okay, so with respect to this optimization, we won't go into much detail because to explain it really extensively, it will take a lot of time. This is a complex topic, and we are still showing some early result of our study. But anyways, let's see what we are talking about. So far, we haven't gone into much detail with respect to how a field is organized in memory. Well, actually, I said before that you have the dense dimension as the last, because you want to achieve the maximum access coalescing. What this means is that when you access a field non-offset, so at the center of your stencil, at the center of your computation, so you have threads taking care of cells, for example, you are accessing the current cell, so you use the thread index to access the field at that cell. So in this case, it's already optimal when you write into the center or you read from the center. There you don't have to do anything more. What if instead you read offset, as you will do in a reduction when you access a field that is on a different location type, or maybe on the same but offset, as we have seen yesterday. So now you have to take into account what is the numbering pattern that you used to index your locations, for example, your cells, with respect to the mesh. So with respect to the geometry, and how this geometry is represented by the mesh, which let's say then in the code is translated with neighbor tables, as we saw earlier. So different indexing patterns, different numbering schemes lead to different performance when accessing neighbors. And we can see 3 cases here that we considered. I will describe you how you do this numbering. So for example, in this case, we named row major. Let's say you do your numbering each row at a time, and you basically just go from left to right to number. Very easy. So you do let's say left to right for each row, and then go to the next row. Instead, if you have instead in this pattern called we call structure numbering, you have you still go through rows, but within each row you first do the locations with the same orientation. So in this case, it's cells. So the upward facing cells first, and then the downward facing cells second. And then you go to the next row and do the same. So the same can apply for different locations, for example, edges or vertices, of course. But we will see that in a second. Let's maybe mention that there's also the numbering that follows a space filling curve. So this curve is employed in this. So you basically give the numbers following the curve. Maybe you cannot see here, but you would go, for example, 1, 2, 3, 4, 5, 6 while you follow the curve. It should be very easy to understand. And as you can see from the shape of this curve, this is meant to increase the locality. So you try to visit neighborhoods and then move to the next neighborhood. You're not doing one row at a time, and you're really trying to increase the locality of your visit. And this turns out that it will have the effect of increasing the locality as we defined it earlier for caches. But okay, let's say that in general, these have implications on performance. They have effects, as mentioned, on the locality and thus the cache efficiency. But they also have an effect on how much coalescing you get, coalesced accesses you get, and thus the usage of bandwidth on many memory transactions per unit of time. Okay, let's start considering an example. So we will see an iteration through the neighbors of 4 cells for consecutive cells, because this is how they are processed when you are considering 4 threads. So I ask you to consider this a warp, even if I told you it's 32, but it's clearly much better to visualize 4 instead of 32. And we will see how this warp of 4 threads that process these 4 cells are going to iterate through the respective neighbors in order. So the neighbors will be cells, again, according to this iteration space, as you can see here. This is on the structure numbering scheme. And let's see, for example, the first set of neighbors. So again, if you think about the code that I showed earlier, here you're accessing, for example, the neighbor table. You get the neighbor index and you use it to access a field on cells, right? So all the threads are always executing the same instruction. This is the assumption because they are in the same warp. So they are all at the same time, let's say, visiting the first neighbor. As you can see, the accesses here are again coalesced. You can imagine also with more cells. These you get consecutive numbers, so fully coalesced accesses, a sequential access pattern. If you go ahead, the second set of neighbor, again, coalesced accesses, fully coalesced, and to the third set of neighbors, same thing. You might notice that, for example, between the first 2 iterations and the third, you are completely changing the set of cells that you are accessing. This is why we can say that with respect to the other numbering scheme, this one has the worst locality, but it always gives fully coalesced accesses. So it's really we are really already talking about trade-off, and in this trade-off, this scheme goes fully towards the coalesced, but gives the worst locality. So another scheme, same iteration space, but this time, since we are considering again 4 consecutive cells, centers, these are of 2 different, let's say, orientations. So like downward and upward. And here we have to, of course, again consider the first set of neighbors and the second. Like for example, this is the first set of neighbor. Of course, it's arbitrary where you start, but I can assure you that it doesn't. Let's say that the first neighbor that you select and the order of iteration doesn't actually affect the performance. It's the numbering scheme that does. Um, so here we can see the neighbors that we are accessing. So you might notice that here you have maybe a stride 2 access. You do 11, 13. So you're skipping 2, 24, 26, the same. And then you also skip a lot here. So access coalescing, well, not so well. On the second set, for example, you get access coalescing. So sometimes you get it, sometimes you don't. Here, again, in the middle. But if we go back, you notice maybe the number of neighbors that we share between each iteration. And maybe you can see that with respect to before, we are improving somehow. There is more locality with respect to the previous scheme, slightly more locality. Okay, let's go back to the structure numbering, but let's consider a different iteration space. So we will look at edges. This is how you number your edges in the structure numbering. So again, go 1 row at a time. First, consider edges with the same orientation. So the horizontal one, then the one tilted this way, then the other tilted the other way. Let's again consider 4 centers, consecutive ones. Now the iteration space will be edge to cell, so we will access cell neighbors. So let's see the first set. Again, structure numbering gives always coalesced accesses. This is a very nice property, but absolutely no locality in this case because you're accessing a completely different set of neighbors with respect to before. Let's see the same iteration, but with a row major numbering. In this case, you number your edges going from left to right, and then next row again. So this is quite more complex to visualize because you have 3 orientations of edges. And so this is the first set. We selected 4 edges, but we got 3 cells selected. Well, this is because also you have 2 edges sharing one neighbor. And this is also a nice property because here you're really sparing 1 memory access for, let's say, per 4 edges. So you also spare some memory traffic here. And again, consider this scheme is a compromise between access coalescing, which you can see on the first set of neighbors, but not on the second. But again, you have some locality, some data locality and temporal locality. And again, this is really a compromise trade-off. Not go into detail with respect to the space filling curve, but just know that, as mentioned, it provides the maximum data locality compared to the other patterns. And so the real benefit here is to have the maximum cache efficiency. However, you can imagine that access coalescing is almost absent. So maybe you can try this with an exercise after you have the slides, and you can really see how this is mapped. if you try what are the neighbors here, the cell neighbors, for example, you will see that actually access coalescing is very rare. Okay, so these were the optimizations, or the optimization that we studied. Let's jump into seeing some numbers. Um, so we tried all of those on a code extracted from icons dicor, which is computing Laplacian and Smagorinsky coefficient, but it's really not important what it computes. So in this code, I can mention that the neighborhoods used, the local neighborhood used is always edge cell vertex, the diamond we saw yesterday. So we took the timings on a 340 by 340 grids with 80 levels on the vertical, so a lot of edges, which is the dense iteration space. We used only one GPU, an NVIDIA V100 accelerator, and CUDA Toolkit Release 10. So the baseline was 13 statements of Dusk, therefore 13 kernels. So we did this, of course, when still Dawn couldn't do this optimization and did everything by hand, so optimize the CUDA code. Now Dawn can do some of this optimization, as we will see, and maybe keep in mind that this is a limited piece of code, and yeah, well, other stencils might give different results, but in general, what we got is promising, as you will see. So this is the time that we got with the baseline. So maybe the scale is not so important. What's important is the how much you can improve in maybe in percentage, and so this green one is the baseline, starting point. Then we applied on top of that the pack vectors optimization, which gave some benefit, some performance gain. Then we do all the optimization on top of each other. So on top of the packing vectors, we fuse the dense loops as so before. So non-offset dependency, data dependency, and offset data dependencies. We try to fuse them all together. And as you can see, you have a trend here, but there is an outlier. And here we think this basically degrades performance. We don't know exactly why. We think it's that some point the kernel got big, and the lower level compiler probably is doing something not so smart. But what is important for us is that the trend is downwards if we do this optimization. Then again, some merging reductions. So maybe here when I say fusing reductions, I also mean fusing the kernels that contain that reduction, which we didn't do before. And these also, so fusing the kernel containing the reduction and fusing the reduction together gave a nice performance again. So we are again in a good trend. So then we fused a reduction and a sparse loop. So this was the last two kernels remaining. We got into one kernel, and this is the performance, the runtime that we got at the end, which you can see it's already less than half than start. We tried recurrent stencil inlining, so there was a computation of dot product between two vectors that was reused by three kernels. We tried to inline that. This, of course, before merging kernels together. So we started from let's say after we applied packing vectors optimization, we tried doing this inlining, and we saw very little improvements. Maybe it's an unlucky case, but as I said, this optimization is not always gives a benefit. So and it's only one case we considered, so we don't have really extensive results on that. What we were surprised to see is how much parallelizing also over the K loop gave in terms of performance. So this is the reference, the one kernel that I showed before. And then if you apply parallelization also over the K, you really gain still a lot. Well, this is because, of course, you increase the number of threads, even if you even though your initial number of threads was very high, because as you have seen, the mesh is big. It's 176,000 edges with respect to the number of cores of the architecture. So the improvement here is really in a better warp scheduling, as I told you before. It's really the latency hiding that does its job. And we measure that, in fact, the average instructions per clock cycles almost doubled when applying this optimization. So we also tried the different indexing patterns, the numbering scheme, row major, structure number, I think we called it, and space filling curve, the one that Icon is using. We reused that. We saw that overall differences were not very noticeable, but the icons one, so the space filling curve was not the best performing. We saw that the row major was the best one. Okay, then we also tried combining all of this together and comparing what we obtained with respect to the original stencil as we extracted from icons, and we took as reference the OpenACC translation of it. And we saw that with respect to that, we can do better. I think this is less than half the runtime, so we are really happy with that. This is on a different accelerator. And this is the, let's say, the promising result. That's what we are doing is can be better than the OpenACC translation. So let's mention then what Dawn currently supports. Fusing dense loops, all the slide that you saw before that had the title fusing dense loop, this is all supported by Dawn. Parallelizing K loops also is supported, and the rest must be considered. As I mentioned before, the indexing pattern is outside the scope of Dawn because it involves the field storages, so the meshing library and so on. Okay, so on Outlook, maybe we are very happy with the results, although they are not maybe extensive. We are not sure if they generalize to other stencils, and this is something we will try, of course, experiment with. We want to also test other optimizations, and still we have to work on Dawn's optimizer to make it support already those that we considered. And of course, as some of you asked, what if you have multiple GPUs or multiple nodes? You need halo exchanges and so on. We still need to consider that in the implementation, but we already have in mind a scheme for which this would work. So thank you for your attention. Any questions?
Oh, Looks like questions are being typed. So let's give everyone some time to type the questions.
I think you can go ahead and read Will's question.
Yeah. So Will is asking, could you point me to the baseline code in Icon? I would like to check how much the code has been optimized since you branched off. I assume you did not make further optimizations to the OpenACC code.
Yeah, that's correct. The last one, we didn't optimize it further. Sure, I can point you to where this is. Of course, we cannot share with all the participants because it's icon. It's protected, but yep, I will do that. I think this was done in August, just to give you an idea. So yes, we will take this offline, of course.
Okay, I think we give participants a bit more time in case there's other questions. Otherwise, I believe a next point on our agenda will be a small break. And after that break, we will be looking into the performance exercises, which will be in a hands-off manner presented by you, Giacomo, if I understood this correctly.
Yeah, exactly. There will be a demonstration on compute node of TSA, which is a supercomputer at the Swiss Supercomputing Center. So we'll see there how we do this optimization manually, and then we compare with what Dawn can do. But then there will be, I will leave you some slides to how to replicate the same at home if you have a GPU or you have access to, let's say, a virtualized a virtual machine in which you have a GPU, and you could try the same there. Unfortunately, we couldn't provide a like a my binder for that. We were not ready for this. Hopefully, yeah, next time.
All right. So it looks like there's no more questions.